Hi, my name is Netta and this is Chemistry at Glance. So if you don't know me yet, I prepare videos with past paper questions, and I also have a blog where I share all I know about AS level chemistry and all the ways and techniques I used when I studied chemistry. In today's video, we're gonna practice some past paper questions on halogenalkanes, the reactions of them and their uses. So I prepared quite a lot of questions about them. They all past paper questions or the questions I found in my WJEC book. These are WJEC questions, but many different examples have very, very similar questions. So even if you're not from WJEC, you can still have a go at them. So the first question says, name the reagents and conditions that could be used to prepare 2-methyl-butan-2-ol. So this is an alcohol, and we can create alcohols from halogenalkanes. And for this, you need sodium hydroxide. So you can have a halogenalkane. You add sodium hydroxide, and the halogen will exchange its places with the OH. So one of the reagents that we need is NaOH. And so let's draw our 2-methyl-butan-2-ol. So it's a but, so we need 4 carbons. We know that we have a methyl group on the second carbon, and we have an OH on the second carbon. That means our halogen group had to be on the second carbon as well, in the place of our OH group. So actually NaOH is our condition. We can't do without NaOH. Aqueous NaOH. And we also need our halogenoalkane. So it has to be the same. It also has to have a 2-methyl group, because this doesn't change. But it also needs a halogen. So you can just write 2-halogen butane, because it can be any halogen. Our halogen could be bromine, iodine, or chlorine. Okay, next question. Why is chlorine more electronegative than bromine? So first of all, what electronegativity is. So electronegativity is the ability of an atom to attract electrons. Obviously, chlorine is smaller than bromine. And because it's smaller, it has one less of a ring around it. So bromine will have one more ring than chlorine has. This means that the nucleus can attract these electrons better in chlorine than it does in bromine. So our answer is chlorine is smaller. Therefore, it attracts electrons better. Next question says, write down in order the steps needed to test for the presence of bromine in an organic compound. Include the results expected. So our test for halogens go as follows. So the first step you have to do is mix the compound with NaOH, exactly as we did in our reaction over there. Next step that you do is you have to neutralize the remaining NaOH, with nitric acid. So after you mix it with NaOH, there might be still some NaOH which hasn't reacted because it was in excess. So you have to neutralize that excess with nitric acid. The next part is you add aqueous silver nitrate. And after you mix it with silver nitrate, if it's a bromine, which we're looking for, you're gonna have a cream precipitate, a cream color. The solution will have a cream color. And after this, if you're not sure about the color, you can also add ammonia. And after you add ammonia, bromine will only be soluble in concentrated ammonia. So this is the test for halogen. So you mix it with NaOH, neutralize the excess, add silver nitrate, and then if it's bromine, you'll have a cream precipitate. If it's chlorine, it's going to be white precipitate, and if it's iodine, it's going to be yellow precipitate. Then, if you're not sure about the color, you can also add ammonia. After you add ammonia, chlorine will dissolve in ammonia, but will be it's soluble in ammonia. Bromine is soluble only in concentrated ammonia, and iodine is insoluble in ammonia. If that was too fast for you, visit my blog. I leave the links in the description box below and you'll understand it better. Next question says, what is the product of the reaction of 1-bromo-2-methylbutane with aqueous sodium hydroxide? So this is the reaction we had at the beginning of this page. So we have our reaction of 1-bromo-2-methylbutane. So butane, we have 4 carbons, 1 bromo, 2 methyl, and the rest of them are hydrogens. I'm not going to draw them, just draw the lines and imagine you have hydrogens all around. Then you react it with sodium hydroxide, which is aqueous. This is important, it's aqueous. And if it's aqueous, our bromine group, butane, still have our methyl group, and our bromine group will be substituted by the OH group from NaOH. And the product, we can name it, it's 2-methyl-butane 1-ol. This is our product. However, the situation is much more different if you're using an ethanolic sodium hydroxide. This means that sodium hydroxide dissolved in ethanol. If this is the case, you still have our beginning product, which is our 1-bromo-2-methylbutane. 1-bromo-2-methylbutane with the hydrogens. You add your NaOH again, but it's not aqueous, it's ethanolic. And instead of substituting our halogenoalkane, the halogenoalkane is completely removed. So you still have 4 carbons. However, if our bromine is removed, you only have 2 hydrogens left. That's why a double bond is created. You still have our CH, actually it was on the other side, so we still have our CH3 group and the rest of hydrogens. That was a substitution reaction. In this case, we have an elimination reaction. The next question. One compound previously used in correction fluid was 1,1,1-trichloroethane, but this has been replaced by compounds such as methyl cyclohexane that has a much less adverse effect on the environment. This is our 1,1,1-trichloroethane and this is our methyl cyclohexane. Explain in terms of bond strengths why 1,1,1-trichloroethane has an effect on the ozone layer, but methyl cyclohexane that's not. Looking at this compound, you can see that you have our CCl bond. This bond in air, when it's hit with UV light, it's broken. So CCl bond is broken by UV light. When it's broken by UV light, you should know from the previous post, from the previous video, that a radical is produced. And this radical makes hole, radical is produced, and this radical makes a hole in the ozone layer. This was all in the halogenation equations with the initiation, propagation, and termination. In the initiation, you had a Cl gas and then the bond was broken and you had a radical formed. The same happens with CCl. The bond is broken by the UV light in the atmosphere. A radical is produced, and this radical is very dangerous for us, but it also makes holes in the ozone layer. It destroys the ozone layer. In methyl cyclohexane, we have no Cl, so even though it's in the air, UV light won't affect it. It won't affect it also because the CH bond is too strong to be affected. So I'm going to write CH in methyl cyclohexane is too strong for UV light. Next part of this question says, heptwanine is an isomer of methyl cyclohexane. Describe a chemical test that gives a positive result for heptwanine but not for methyl hexane. So this was present in this topic, the test for carbon-carbon double bond for alkenes. As you can see, our methyl cyclohexane has no double bond C bonds, so we have to find a test for our alkene. One of them is adding bromine. The CC bond will be that's decolorized. This means that if a bromine is added to an alkene, the bromine color will be decolorized due to this carbon-carbon double bond. Because methyl cyclohexane doesn't have a carbon-carbon double bond, it will not be decolorized and the color of bromine will still be present. In this question, we are asked to draw the mechanism of 2-chloropropane reacting with aqueous sodium hydroxide to produce an alcohol. So, the mechanism starts with 2-chloropropane. Propane, so 3 carbons, 2-chloro, so chlorine in the middle, and our hydrogens. Let me draw the hydrogens as well. And we know that it's reacting with aqueous sodium hydroxide. It's aqueous, so in this instance, it's going to be a substitution reaction. So we have our OH. So in this mechanism, C and Cl experience a heterolytic bond fission. This means that they're not sharing the electrons equally. Chlorine is more electronegative than carbon, so it wants the electrons more to itself. That's why it's slightly minus. And carbon is slightly plus. Because carbon is slightly plus, it's exposed to electrophilic substitution. This is an electrophile. Electrophile wants to a nucleophile. Nucleophile is basically electron loving. No, it has too many electrons. It wants to get rid of these electrons. Sorry, I got confused for a second. This is a nucleophile. It wants to get rid of its electron. It wants to share these electrons. And carbon is exposed to nucleophilic attack. Because it's positive, a nucleophile, which has all these electrons, will want to bond to this carbon and share these electrons with it. And that's exactly what it's doing. You have to draw an arrow to show the movement of these electrons. So, we still have our propane, but chlorine is substituted with our OH group. Because chlorine took over most of these electrons, so it's much more negative than carbon, it separates and it goes on its own as a chlorine minus, while carbon is very, very positive, and when nucleophile is around, it will hop on, take the place of chlorine, bond with carbon, and chlorine will go on its own. And this is our last question. It's a very long question. It might be very confusing, but I hope I can explain it well. It is possible to test for the presence of halogen atoms in halogen alkane by hydrolysing the molecule and testing for the halide ion released using silver nitrate solution. The hydrolysis of 3 compounds was performed under identical conditions, and the time taken for a precipitate to form was measured. The results were as follows. And then the carbon-halogen bond energies and the electronegativity differences for each bond are given below. Now we're asked to use both tables to comment on the factors that affect the rate of reaction. So the rate of reactions are affected by both bond strength and electronegativity. We can even do a table out of this. But they are more affected by bond strength than electronegativity, and they both work against each other. And that's what I'm going to explain to you now. Okay, so by looking at the average bond enthalpy, you can see that it's the smallest for carbon iodine. So the carbon halogen bond is weaker as the group descends, because in the periodic table you have chlorine, then you have bromine, and then you have iodine. That's how they go in this. They all the same group, but they all like period lower. And for carbon iodine, you can see the bond enthalpy is the smallest. This means that the least amount of energy is needed to break carbon iodine bond. This also is shown in the time for precipitate to form, because for 1 iodopropane, the time for precipitate to form is less than 1 minute, which is much less than 17 minutes for 1 chloropropane. This means that bond is weaker in C iodine than it is for C chlorine. So concluding, for bond strength, C halogen bond is weaker as you descend the group. Less energy needed to break the bond as you descend the group. So as you go down for Ci, the energy to break the bond is smaller. This agrees with our first table, which says that 1 iodopropane, for 1 iodopropane, we have to wait less than 1 minute for the precipitate to form because the bonds are weaker, so they're easier to break. However, the electronegativity changes our situation. You can see that the electronegativity difference decreases as you descend the group as well. There are the values right there. The more electronegative the bond is, the more electronegative it is. So chlorine is the most electronegative out of these 3. So as our table shows us, so in this bond, carbon will be the most positive. If chlorine is the most negative, then carbon in this bond has to be the most positive out of these 3, which means this bond will attract a nucleophile the most, because carbon will not be more positive with any of them than it is with chlorine, so it will be easier for carbon to attract this nucleophile, this OH that we had a look in a previous question. So to conclude, electronegativity descends as we go down the group. Carbon and carbon-chlorine bond would attract the nucleophile the fastest, therefore should react the fastest. However, our first table shows us otherwise, that actually iodine reacts the fastest. This explains our confusion with both bond strength and electronegativity. It basically shows us that bond strength has more power, decides on the strength of the compound rather than the electronegativity. Because you would imagine chlorine would react the fastest, the one chloropropane would react the fastest because the carbon would easily attract that nucleophile. However, the carbon-chlorine bond needs the most energy to be broken. So bond strength takes over. And to conclude, we can say bond strength has a bigger effect on the compound than electronegativity. And this is all you gotta say. This would be a big question in the exam, so it'd probably be like 6 marks or so. This was all I had for this topic. So remember, everything I show you are my techniques and ways of learning and revising. If you have any questions about my videos, please comment or email me. I leave all the links in the description box below. Also, if you have any comments about the quality or content of my videos, please also leave them under this video. Thank you. Like, subscribe, and see you soon. Bye.